Welcome, I'm Perdita Stevens from the University of Edinburgh, and this is a recorded version of the keynote talk that I gave at the Educators Symposium of the MODELS' 2018 conference last week, entitled Teaching and Learning about Abstraction. This is the picture that I put up on the projector while people were coming in to give them a chance to mull it over before we actually got going. We'll come back to it later in the talk. You might like to have a look at it and ask yourself questions like, what does this have to do with teaching and learning abstraction? And what kinds of rules does it obey? And what kinds of rules should it obey? We'll come back to it in a moment. So, when I got the invitation to give this talk, this was the kind of plan that I came up with initially. And of course, the first thing I have to say is that I'm principally a researcher in software engineering, not in education. And so this was a good opportunity for me to dive into the research literature on teaching and learning about abstraction, and it's been great fun, and I hope to share some of that with you today. But inevitably I've missed lots of interesting stuff, and it's possible that I've misunderstood some things. And of course, if you think either of those is the case, then I'd be delighted to get an email from you explaining it. Well, more delighted if I've missed interesting stuff than if I've got stuff wrong, actually, but either way. But of course I had a lot of opinions about teaching and learning about abstraction, having done stuff that involves it for several decades now. And so here's a bunch of stuff that I knew before I started. I knew that abstraction is key to software development. And I knew that we have to make a careful distinction between using abstractions that are given to students and creating their own abstractions, because using abstractions is relatively easy and creating abstractions is harder. And I knew that this is important because people who are better at abstraction are better at software development. And indeed, further, I knew that learning software development largely is learning how to use and create abstractions. And therefore I knew that it's really important for us to be good at teaching these abstraction skills. Well, as so often, it turns out that it's all a wee bit more complicated than that. The first thing hardly needs to be said to an audience of people who are involved in modelling, but there are other audiences to whom it would need to be said, so let's begin by pointing out that abstract is by no means the same as vague. When we abstract stuff away, it's really usually rather important that we know precisely what we're abstracting away and what we're keeping. And we can do just as precise reasoning on an abstract level as we can do on a concrete level. This might be slightly more surprising to you. It turns out that there's an important distinction to be made between abstract thinking and thinking with abstractions in the sense that we typically want students to do in software engineering. And my claim is that abstract thinking is necessary but not sufficient for students to be able to succeed in this area. So let's say a bit more about that. Here is the kind of abstraction process that we probably all have in mind when we think about abstraction. We start off with a concrete domain and we remove some details, or we withdraw attention from some details that are not important for some particular purpose, as I prefer to say. Another way to think about this is that we make some generalizations and form equivalence classes of things that between which we don't want to distinguish for some particular purpose. But when people talk about abstract thinking in the literature, they're often talking about something more like this. They're talking about reasoning on the abstract domain, doing some stuff at this point, whether it be refactoring or whether it be making some deductions or whatever. We're talking here about thinking which is not directly tied to a concrete context, and this is the distinction being made. Now, of course, this is important to us in software engineering as well, because generally speaking, that was the point of making the abstraction. It was in order to be able to do some stuff in the abstract domain that it's not reasonable to do, for whatever reason, in the concrete domain, usually because there's just too much information in the concrete domain and we can't keep hold of it all at once. But there's always a reason for students to do this. We typically want them to be able to put the whole thing together rather like this. We want them to be able to form an abstraction and do some stuff at the abstract domain in order to then be able to go on and do the corresponding stuff at the concrete side. For example, we might want them to make a diagrammatic representation of the architecture of their system so that they can see that they've got too much coupling going on, so they can redesign it at the abstract level and then make the corresponding refactoring also at the code level. But before we come back and look at this kind of picture in some more detail, let's first of all pay attention to the right-hand side of the diagram and think about abstract thinking and how people learn to do that. And no talk of this nature would be complete without some mention of Piaget, or to be more precise, Inhelder and Piaget and their work in the 1950s. I'm sure you've all seen at some point this list of 4 developmental stages that they claimed children go through sequentially, the first 2, sensory motor and pre-operational, being stages that rather young children go through. The concrete operational phase then lasting up to, Piaget said, about age 12, and that being the point at which people can make deductions and do reasoning in a fairly concrete context. Leading on to the stage which we mostly think of as being important for formal mathematics and for computer science, and which the literature takes to be the point at which those things can be done, the formal operational stage. And this entails things like being able to reason symbolically, being able to make scientific hypotheses and investigate them systematically. Abstract thinking in that kind of sense, general thinking, being able to form general conclusions and understand the relationship of evidence to it. However, even though I don't know very much about this field, I do know that it's very important not to follow Piaget in an uncritical way, because there's been a great deal of work that has gone on afterwards. So although Piaget has been incredibly influential on the field, he's not the last word. The stages are at least blurred, and although Piaget talked about people entering the formal operational stage at about age 12, that has proved to be quite controversial and a bit more complicated than that, and even the question about whether people ever enter the formal operational stage turns out to be not as simple as you might think. So one finding was that only about 35% of adults have entered the formal operational stage by some measure. Part of what complicates this is that it turns out to depend really quite a lot on how you look, and this quite often seems to happen in developmental psychology. So that there's it's not directly related, but there's a lovely finding which I remember concerning conservation of number. So you've seen probably the claim that young children can be fooled by if you take a row of objects and then you spread the objects out a bit more and you ask children, are there the same number of objects in this row as there were to start with, or more or fewer? Very young children will look at the row which is now longer and will say there are more objects in the row now, even though they've seen you spread them out and they know there are the same number in some sense. Whereas older children will correctly say spreading them out hasn't made any difference, there are the same number. Well, it turns out that the original experiments were done here by the experimenter spreading out the items, and if you instead have a naughty doll spread out the items, then children can give you the right answer much younger. So it was not so much perhaps simply conservation of number going on as maybe very young children assuming that if the experimenter was asking them this question in this very serious setting, then there must be something to observe, and so the answer must be that there are more. So things are sometimes more complicated than they seem, and in particular how you test what stages people are at turns out to be quite important. Of course, lots of other people have built on this and done further investigation. Adey and Scheer seem to be particularly important. They found that only a minority of children follow Inhelder and Piaget's sequence, and one of the things that they did that turns out to be important in the literature was that they developed and validated tests for the presence of people at particular stages, the pendulum test being one of them, in that children have to investigate the effects of things like the length of a pendulum string and the weight of the bob and so on, and form hypotheses. I'm not going to go into that any further because it's not my field at all, but let us start to come closer to our own field and say, well, does it matter? Well, I already alluded to the idea that formal operational reasoning is associated with mathematics and with computer science, and indeed this is a lot of the received wisdom. This is a quotation from a 2003 paper by the people whose names you see on the slide there. Many other studies have shown that formal operational reasoning ability is necessary for success in procedural computer programming and logic. Now it's notable, I think, that all those studies cited there come from the 1980s, and you may notice that that's notable for being a little while before we started to carry out as a matter of course teaching in computer programming and logic to children a lot younger than 12. So we may be slightly suspicious about this. And indeed, Benneson and Casperson have done a sequence of very interesting papers in which they find repeatedly things like this, that there's hardly any correlation between the stage of cognitive development, the abstraction ability in the Piagetian sense, and final grades in CS courses. And they looked quite hard and they just didn't find it. And that, of course, is consistent with the idea that it is indeed possible to teach primary school children to program, which we now find is so. So these are deep waters, and one hopes that psychology professionals are continuing to investigate it. But I think what we need to do is to take even a further step back and say, well, what exactly are we claiming, and why is it that we care about it? Well, here's one possible claim. We might claim people who are good at doing something involving abstraction tend to be good at some software task we care about. And we might care about that because we might want to be able to identify people who have strong potential to learn how to do software tasks. We might want to recruit students who will do well in our courses, or if we're working in a company, we might want to identify employees who will respond well to training in some software task. Indeed, even if we find a very close connection between those things, we might even be able to say if it's cheaper to test somebody's ability to do the thing involving abstraction than it is to test their ability to do the software task, we might even be able to use this connection to track somebody's development. And of course, in the process of understanding the connection between these things, we might end up understanding something about the software task, and that might be interesting and perhaps even useful in its own right. We do have to be a bit careful, of course. It may be tautologous if we care about the abstraction task itself, and even more so, it may be simply unhelpful. So correlation is not causation. This is the absolute key thing to know in this whole field. It may be that we're identifying clever people who are good at both of those things because they're clever, or people who are scoring highly in our tests because they are very compliant with annoying researchers' testing, or some other reason. And I'm tempted to say we're just identifying clever people or whatever, but of course identifying clever people is a major undertaking in its own right. It's just that it's not really one that's specific to software engineering or modelling. Here's a different possible claim. We might want to claim that teaching people in such a way that they get better at doing something involving abstraction tends to make them better at some software task we care about. Now notice that that's different from just saying that these abilities are correlated. And we might have a different motivation. We might think that we can exploit this fact in order to give a cheap or effective way to improve students, or indeed employees, performance on the software task that we care about. We can teach them about abstraction, and thereby they will become better at software. And again, of course, understanding the software task may also be a secondary motivation. But we have to be very careful here not to demonstrate something with an existential quantifier and conclude something with a universal quantifier. And there are three different places in this claim where we might make that mistake. So the danger is that we do one experiment that involves one kind of teaching, and we show that people who get better at doing one thing that involves abstraction get better at one software task that we care about, and it's by no means clear that that would generalise to all the other settings in which we might want to have it. And a difficulty in both of these areas is that we can only talk about what we can measure. In order to answer any of these questions, we need to have a decent way to measure how good people are at whatever we want to mean by abstraction. And at this point we really haven't. So Jeff Kramer, and in this instance his co-author Hazan, have thought about this a lot and talked about it a lot, and this is the latest substantive paper that I could find from them on this. It's about assessing abstraction skills, and it was an attempt to investigate how it is best to investigate the abstraction skills that software engineering students have, and it was basically a survey. It involved identifying a bunch of question shapes and asking a bunch of software engineers and educators which questions they thought were a good test of abstraction. And the idea was to lay the groundwork for a generally usable test. As far as I can see, that hasn't actually arrived up to this point. And the existing literature at this point uses many different tests, and they definitely don't all measure the same thing. In fact, even worse than that, we find in some cases the same test being used in one study as a measure of students' abstraction ability, and in another study as a control test, in order to make sure that they were not just measuring general intelligence with some other test that they claimed was measuring abstraction ability. And that starts to get us to something that turns out to be quite important in this area as an important confounder, which is quite difficult to talk about because it's kind of not politically correct to talk about it, which is that there's a very strong tendency for people who are good at one thing to be good at another. And so if you want to claim being good at abstraction helps you be good at software, you have to be careful that you're not just identifying an instance of that. Unless, of course, that's relevant to what you want to know. So let's think about how you might research this stuff. Here's one possible research plan. If what we're trying to do is to find out whether it's a good idea to select students who are already good at abstraction, then what we might do is we might start off by taking some students and testing their design ability and testing their abstraction ability. And then we might teach them design, and then we might test their students' design ability again. And what we'd be looking for in this case is some kind of sort of dose-dependent effect whereby the better the students are at abstraction, the more thoroughly they absorb the design teaching. So we'd expect to see that the students who improve their design ability most are the same students who start off with the greatest abstraction ability. And indeed, there is literature that studies this kind of thing. Unfortunately, I'm not citing particular papers at this point, by the way, because I don't have space within a talk to address them fully, and so it seems to be unfair to cite particular studies when basically what I'm doing is saying, oh dear, they don't really answer the questions. But I am thinking of particular studies at each point in this talk. So one thing I've seen is papers that ask a rather less interesting question. So in one case, what they do is they start off by saying the student's design ability and abstraction ability turns out not to be correlated at the beginning of the study, but after having been taught design, their design ability after the teaching is correlated with their initial abstraction ability. But we don't particularly see a dose dependence effect there, so that's not quite what you want to know, really. There is, as I already mentioned, a difficulty about how you test abstraction and whether it's really testing the thing you wanted to test. But even more important, they have a problem which is a very common problem in the software engineering education literature, I think because it's usually done by people like me and like most of you who are really only opportunistic education researchers, and so we have access to a group of students that we have to teach for other reasons, but we don't have easy access to a control group of students that we don't teach, and therefore there isn't a control group. And so in this case there wasn't a group of students who were not taught design in between this pre-test and this post-test, and you really want that, because students may very well improve if you give them the same kind of test twice separated in time. They mull it over and they may well get better at it, and you really want to be able to demonstrate that the teaching has actually caused them to do something other than just that ordinary test, retest improvement. So here's another possible research plan. If what we want to know is how to teach abstraction, then obviously a reasonable thing to do would be to test students' abstraction ability and teach them about abstraction, and then test their abstraction ability again and ask the question, well, do their abstraction ability scores improve? And this too has been done. Again, we see the problem of lack of validation of the specific test and of there being no control group. But in fact, in this case, in the cases I could find, you don't get significant results anyway. So via a reasonable intervention, it doesn't turn out to be that easy to actually improve students' abstraction ability. And actually, that shouldn't really surprise us very much, because the ability to work abstractly, to do abstract thinking, is a very large part of what we mean when we talk about having a high IQ. And I'm going to take a wee bit of a digression at this point to talk about this lovely book by James R. Flynn, which I strongly recommend. So Flynn is the person who gave his name to the Flynn effect, which, as you may know, is the effect whereby over many decades, possibly ending in the last decade in developed countries, IQ scores have been steadily rising at a rate of a few points a decade, such that in order to maintain the average at somewhere near 100, the tests have to be constantly rescaled. And this has been happening at a rate that's far too fast to be anything to do with genetics or selection, and it was very unclear why. And Flynn, who's thought about this a lot, points out things like the subtests of the standard IQ tests, where scores have improved the most, are those that seem to involve abstraction the most. So they're to do with having students look at symbols and spot patterns in them and be able to apply the same patterns in new contexts and so on. Whereas if you look at subtests like vocabulary and arithmetic, the rises are much less remarkable. And so Flynn contends that essentially what's been going on is that the environment that children in developed countries all share has itself been developing and changing such as to encourage the development of abstraction skills in a much stronger way than it used to, and that is the effect which explains the rise of IQ. Now, we can of course argue about whether IQ tests measure anything other than the ability to pass IQ tests, but it's undeniable that they are very influential in a very large number of places, and that there's a great deal of demand in the market for techniques that enable people to improve their IQ scores, whether or not that actually enables them to improve their skills in anything that people care about directly. And so the effect is that if you thought you had a way to actually improve people's skills at abstraction in a general way that was transferable from test to test and would actually be persistent, and especially if you thought you were able to do it in a single course or even a single lecture, you wouldn't be an academic in software engineering. You'd be out making millions, if you had any sense, with your genuinely successful How to Raise Your IQ course. In fact, I think the market for that is probably measured in billions of appropriate currencies, not millions. So we shouldn't be too surprising that it's not so easy to give students one lecture on abstraction and then have them be better at abstraction forevermore. However, in model-driven development, fortunately, we genuinely do care about tasks that involve doing some abstraction, and so we can legitimately ask a much more concrete question. We can ask for a particular task that we know is important, how can we help people get better at that? So let's think some more about what's going on there. Well, the fundamental problem of software engineering is too much information. This is why software engineering is difficult. There is too much information in even a moderate-sized software development project to fit in a single human brain. And so, as software engineering has improved over decades, and as we have come out of what was called the 30-year software crisis, I think it's reasonable to look at the ways in which we've improved our techniques for software development and identify this as a common thread, that all of these improvements are really about getting chunks of processing done within the limited capacity of an individual human brain. So abstraction is important on every level. We now have, compared to the 1960s, languages that better support abstractions and verification techniques that rest on this, and we understand how to better use interfaces and how to do unit testing via those interfaces, and of course for models people we understand how to separate concerns into different models. But I think you can even see the advance and success of agile development methodologies as being another instance of the same thing. So when you say we're not going to worry about all the requirements that the user might ever have, right now we're only going to worry about the requirements that fit into this particular bounded small release, and to the rest we're going to say you ain't going to need it. We're doing exactly the same thing. We're saying we're going to identify the things that the humans need to focus on right now, and we're going to give them permission and facilitate them in not focusing on all the rest, and that way we'll actually get some things done. So turning to models, here is my favourite one-sentence definition of a model, which I've been using for some decades now, and here is this word abstract again. A model is an abstract, usually graphical representation of some aspect of a system. And the word abstract gets there because separation of concerns is so important to us. In fact, going further, abstraction and separation of concerns are really two words for the same thing. So you will see people in other areas of software engineering talking about abstraction in terms of levels and talking about how abstract something is. But actually I think that's the wrong question. I think the question for us is, what are we abstracting? It's not so much about levels as about purposes. You make an abstraction for a particular purpose, and that lets you keep the details that are important for that purpose, however minute they might be, while throwing out other pieces of information, however large they might be, that are not relevant to that particular purpose. And of course the name of the game for us is to be able to build software by combining abstractions. So this is the picture that I drew some time ago and have vowed to myself appears in every talk I give since then. I'm not sure how long I can keep it up, but I can just about fit it in here. So what we've got here is different stakeholders in the software system, each working with their own model. To some extent this happens already, but my claim is that this really must happen a lot more as we go on to improve software development. So perhaps here we've got two different groups of users of the system, each with a model that describes the system from their point of view, abstracting away anything that they don't see or care about. And down here we've got a group of perhaps rather mathematical people, judging by the Greek symbols. They're doing some kind of safety analysis of the system perhaps. And the vision is that we have these magic coloured wires, which might be bidirectional transformations, that are combining all these abstractions into deployable software that gets piped over there. And of course, there are lots of very challenging questions about to what extent is it really possible for each group of stakeholders to work just with their abstraction. What kinds of questions can they answer using just their abstraction in a reliable way? And to the extent that their model has to be affected by other people's models, how do we facilitate that in a way which isn't confusing? And I could talk forever about stuff like explanation and negotiation, and there's a whole lot of interesting research to be done there, but it's not the topic of this talk. So let me move swiftly on to something which is actually a little bit of an aside. It's important to be aware, I think, that some abstractions are much more comfortable to us than others. Some abstractions are quite formal objects because they relate to definite formal artifacts. You don't have to be able to read this, which is why it's fine that you can't. But if you've got a bunch of code and a bunch of class diagram, and you can make a purely mathematical notion of what it is for them to be related via an abstraction. Whereas other kinds of abstractions, which are at least as important, are much less comfortable to deal with. Anything involving the real world is quite tricky. And it's tricky in particular because we get this kind of triangle situation. We like to think that you might start with the real world and then sort of abstract some kind of model of it, and then build some code based on that model that will do the right thing in the real world. But of course the code is only correct if it really does interact with the real world properly, including with respect to the things we abstracted away in the model, and it's all difficult to validate, and there are a whole lot of other issues there. But that's all I'm going to say about that right now. Let me go on now back to this picture that I started with and talk a little bit about how I teach stuff that involves abstraction. So the context I'm going to talk about is my course, which is aimed at third-year undergraduates, although I also have fourth-year undergraduates and master's students on it as well, the title being Software Design and Modelling. And this course was strongly influenced by a lot of discussions that I had in the context of writing that paper that came out of the Educators Symposium in 2013. Because up to that point, I had, having had some early experience on teaching modelling, using modelling tools of various kinds, I had moved over to teaching modelling in fairly precise sense, but on paper, and also encouraging students to be very aware of the fact that sometimes you want to do very precise modelling, and other times you're using models in a much less precise sense as informal communication devices, which I still think is important. But in the course of lots of discussions leading to that paper, I began to become re-aware of the advantages of using tools in teaching about these things, and so when I got the chance to argue that the course should be replaced by one which was twice as large in terms of the amount of students' time that it took, I took the opportunity to take what I saw as some of the most interesting things out of the other courses that are discussed in that paper. And so what I do now is I start off from the very first lab talking about consistency, about having a relation between some text and some diagrams. And so I use UMPL. I use UMPL online in the very first lab with the students, because that helps students to get over the very first hurdle, which is the idea that you could have a textual representation of the same information which is also presented in a diagram. For example, the diagram can be just as precise as the text is, which in my experience students sometimes find difficult to handle. And then you can also use the code generation facilities of UMPL online and discuss the relationship between that and the things you've started with, and that gets us off to a good start. And then the first in-class exercise I do with them is what I call the paleo example. It's based on that picture that I put up to start with. So I came across this image, just posted as a standard kind of meme, on Facebook a few days before I was about to teach a version, actually of the previous course, not the SDM course, in which I was wanting to get across the ideas of domain-specific modelling languages and think about what that has to do with class modelling. And in particular I wanted to talk about the relationship between an utterance in a domain-specific modelling language and a collection of objects that conforms to a class diagram. And this just came into my life at exactly the right moment, because what I do with students now is I give them this picture and I say something like, imagine that you are working for a startup and you've decided that your business is going to be quickly producing apps to support the latest fad diet. That can be sold as add-ons to the latest diet book or something, and so you want to be able to provide a way for your clients to specify their diet that you can then quickly take in an electronic form and turn into an app. And this is an example of the kind of thing that your client might give you that you would want to be able to act on. And so then people can see a diagram like this as both being a model in a domain-specific modelling language for describing diets, and also they can see it as a visual representation of something that ought to turn out to be a collection of objects that should actually exist in their application, and therefore which has to have a collection of classes for those objects to be instances of. And I find that makes the connection really quite nicely. So I ask them to start off by identifying what kinds of things there are in this diagram, what kind of different elements are there, and how are they related, and what are the rules about how they can be related. In other words, to draw a class diagram for the system that they're going to build, which we can then point out is also a meta-model for the domain-specific modelling language that they are designing. And students tend to find this quite approachable, and sometimes they produce exactly the kind of thing that I would quite like them to produce. So a couple of things are going on here. We see that we've captured the idea that there should be exactly one yes arrow and exactly one no arrow from every question, and we've also captured the slightly interesting idea that because you don't know whether your yes and no arrows are going to another question or to a result, you have to be able to handle both in some reasonably uniform way to allow for arbitrary depth trees, for example. It's useful to abstract out a common superclass of node. And by the way, one of the reasons I really love this example, have you spotted it? It doesn't actually obey that rule. If you ask is it a fruit or a vegetable, and the answer is yes, you don't know whether to go to is it a potato or to is it corn. Which is beautiful as an example of stuff like, well, why might you actually want a domain-specific modelling language with tool support to help your users express this stuff? So sometimes it goes on beautifully like this. Other times it comes out less beautifully. You may or may not be able to read this, but what went on here was that a particular group of students absolutely insisted on having a class edge in their diagram, which it turns out makes it much harder to enforce that idea that there should be exactly one yes answer and one no answer to each question. But that, of course, was a very rich setting in which to discuss such things, and we eventually went on and refactored the diagram into something more like what you saw on the previous slide from another year. And of course you can go on and discuss a whole lot of other stuff. I always use the example that you probably don't want to have cycles in the diagram, and then that's a nice example of a thing that's not very easy to represent in a class diagram, and it's a motivation for wanting a constraint language to go along with it. And you can also get into all sorts of interesting ideas about, well, can we verify that each question is actually useful in some way, that we don't just have kind of isomorphic subgraphs leading from the yes and from the no arrow out of a given question. Let's go back now to thinking a bit more about the simultaneous use of different abstractions, and in particular the simultaneous use of concrete representations like code and abstract representations like class diagrams. This is, as I kind of came in describing, something which turns out to be really important in our field, and here is Newth saying so. One who is a natural computer scientist can rapidly change levels of abstraction, simultaneously seeing things in the large and in the small. And the same kind of phenomenon comes up in that paper cited there, where they, as the title suggests, studied how software designers interact with sketches at the whiteboard. They found that designers frequently jumped between thinking about minute details and thinking way up at the architectural level. This is a thing people have to be able to do. Why is this important? Well, in an ideal world, you want to be able to have a single abstraction and do all your reasoning at that level, and then have it automatically tell you the answer to the same question, if you like, at the concrete level. But the kinds of abstractions we're working with and the variety of questions we ask of them doesn't always lend itself very well to that. So here is a clip from an interesting essay by Friedrich Steinmann, which is about to appear at the time I speak in Onward, but he very kindly sent me an advance copy of it when somebody mentioned to me that I should read this if I was talking about this subject. And his point here is that you might naively say, well, a good thing, an abstraction you can do is to abstract away the subclasses of a given class and not pay attention to them, and just look at the abstract base classes. But of course, depending on how you interpret that rather vague instruction, you may get something that's nonsense, as in case B, or you may get something which is, for a certain class of questions, is misleading. So for example, if you use this as an abstraction of this, then you have lost the information that not all components can in fact have children. And really what you want, it turns out, is something more like this, but that's not completely obvious from the naive description of how you might use the abstraction, so you have to be careful. Here's another example which I've come across in my own teaching. Students find state diagrams quite approachable because, after all, they've typically seen something like finite state automata earlier on in their computer science career before they come to modelling. So they know stuff like, well, if you start in state A and you do an F and get to start state B, and then you do a G and come back to state A, that's a no-op, isn't it? Well, yes and no. What is actually going on, of course, is that you start in some concrete state which abstracts to abstract state A, and then you come back to a possibly different concrete state that abstracts to the same abstract state A. But if students mistakenly think that they've come back to the very same concrete state, then they can go badly wrong. And of course, if we are expert at jumping between levels, and we understand this very well, then we may not even notice we're doing it, and that can lead to confusions. So let's formalise this a little bit. What we expect to be able to do is to start off with a given concrete state and abstract it to some abstract state, maybe a state in a state diagram or whatever, and do some kind of manipulation, go to a new abstract state. But then, in order to know what the corresponding thing to do on the concrete side is, we need two pieces of information. It's not enough just to know A primed, the new state in the state diagram or whatever it is. We also need to know the original concrete state. And that, by combining those two pieces of information, we can have a reasonable expectation of knowing what's happened on the concrete side as a result of knowing what happened on the abstract side. Now, of course, those of you who, like me, spend time thinking about bidirectional transformations have already recognised this diagram. You've said, it's a bidirectional transformation. Specifically, it's a lens. But for anybody who hasn't seen this before, let's point this out a little bit slower. What's going on here is that we have if you like, a one-argument function from a concrete domain to an abstract domain. In order to know how to go from C to A, we only need to know C. Okay, we just have a function from concrete to abstract. But along with that goes a second function, which is the one that tells us how to do a corresponding update on the concrete side to an update that was done on the abstract side, and that you will formalise as a two-argument function. So we say that the one-argument function is a get function, this is in asymmetric lens terms, and we say that the two-argument function is a put function. It tells you how to put back the change. So we have an asymmetric lens, which we might call abs, but between C and A. Now, I think what this does is it shows us one of the reasons why using abstractions is already hard, even before you get into issues about creating your own abstractions. It's the very fact that the put function requires two arguments. We have a tendency to give students the get function, to say this is how you form the abstraction, this is what it means to be a class diagram of a system of code, for example, and assume that that's enough for them to be able to construct and use the put function. But actually the put function is quite a complicated beast at times, and so it's not too surprising that people may find it hard to do in their heads at times. This also gives us a framework in which to distinguish between the use of a given abstraction and the creation of an abstraction, which I mentioned right at the beginning. And this turns up as the question of, well, who programs the books, the bidirectional transformation? A lens is a kind of bidirectional transformation, by the way, and I usually use the bidirectional transformation terminology. So engineering with models, for example in UML, mostly involves using a given abstraction. So the abstraction that relates code in a class diagram, for example, is pretty fixed, and students just learn it and can learn how to use it. Although this does shed some light, I think, on why sometimes state diagrams are particularly difficult to use correctly, and it is because that is the place in ordinary modelling where people have to be able to form their own abstraction. So students will often say, how do I decide how many states there should be in this state diagram? And when you ask exam questions about this, you quite often end up having to give guidelines along the lines of you should expect to find about this many states. And the reason is that actually there are lots of different correct ways to write state diagrams for the same given system, depending on which abstraction you pick. And so we tend to say things like, well, you should put into the same abstract state the concrete states that have qualitatively the same behaviour, but this is really a kind of informal notion. And of course, as soon as we go on to wanting to talk about things in language engineering, wanting to talk about the design of domain-specific languages, for example, then we're asking students to engineer the abstractions themselves, or we might say in another setting, to program the bidirectional transformations themselves. And so perhaps we might say that it's this need to work across levels of abstractions that explains the earlier negative results, that they weren't looking for the right kind of abstraction skills or doing the right kind of abstraction teaching. And we might say that if we teach people explicitly to work across abstraction levels, we train their abstraction skills in that, maybe that will help them to do software better. But I think even here we can justifiably be quite cynical, because if that were really going to work, then it ought to be the case that these kind of skills of working across abstractions are highly transferable and indeed highly transferred. So it ought to be the case that people who are good at working across multiple levels of abstraction in one kind of task setting are also good at it in another task setting. And actually I don't think this is right. Is it really true that all the great model-driven development practitioners you know, who are naturally expert at working across multiple abstraction levels in that setting, are they all brilliant at putting IKEA furniture together, which involves relating the real-world situation of the furniture and the abstraction in the pretty diagram, or are they equally brilliant at cooking? Because that's not really my experience, and yet I think in terms of abstraction they both require rather similar skills to the ones that we see in software. So I think that learning this stuff may be much more context dependent than we sometimes tend to think. So I've got a few slides of kind of final thoughts. One thing is, I have so far taken on trust that what we're really talking about is abstraction, which is a function. So I gave you an asymmetric lens with a one argument get function, and I've been talking all along about mapping via a function from the abstract domain to the concrete domain. But in another setting I might not do that, and I think it may be a better way to look at it to say that we're really talking about consistency and the maintenance of consistency. In fact, I think I would go so far as to say that in computer science in general we think about functions too much, and we really ought to think about relations more. But I'll leave that hanging. Second set of final thoughts is, well, teaching and learning, although we tend to put them together like fish and chips, they're not the same thing. Well, I mean, duh, I don't need to tell you that they're not the same thing. But it may be that one aspect of that that's important here is that there may be some kind of cargo cult thinking going on here. I think it may be that we know that as individual learners, our journey to understanding stuff has involved some important aha moments about abstraction. So we know that learning abstraction is important. And so we maybe feel that if only we could teach students that directly, they would be able to get to where we are in a more efficient way. But I think that that's not necessarily the case. We talk about transferable skills, it's very fashionable to do so, but we know that transferable skills are not always transferred, and we already saw in the early look at Piaget that the results you get can depend a lot on the way you ask the question, and it may be just that there's no royal road to understanding abstraction, even if we think, you know, everybody who gets really good at model-driven development, you know, eventually learns to understand abstraction really well. That doesn't follow from that we can realistically teach it to them. It may be that that has to be emergent from a whole bunch of experience that they have with particular abstractions. And a third and final set of final thoughts is that although sometimes using a particular abstraction is plausibly justified by the context, I don't actually think that's the whole story. I have the feeling that actually individual preference and maybe even individual self-image, as for example a mathematician who likes category theory and does things as abstractly as possible versus a practitioner who likes to have their hands dirty and worry about details, may matter very much to how we do particular tasks. So some people see using minimal representations as, you know, not just convenient but actually as a moral good, whereas other people see including realistic detail as a moral good. And this is something that I've come round to think actually as partly as a result of writing and reading a whole lot of reviews on papers. So I see different people think different things about the same paper, including about my own papers, I have to say. So I tend to write papers that have rather pared down abstract examples that to my mind illustrate the key point. And sometimes reviewers complain about this and they say they want bigger and more industrial examples, and I end up feeling, well, I write the papers I want to read, and when I read other people's papers I often get frustrated there too, because they give me what seems to me to be extraneous detail that does nothing but make it harder for me to read the paper, and I wish they would pare it down to a more abstract example. And while of course I accept that there are lots of ways of doing this wrong, and that if you're going to use an abstract pared down example, it's really important to explain what you think it's doing and how it would relate to real settings, I do think that part of what's going on here is individual preference. And I think that that's a very general fact as well, and it influences people's work in all kinds of ways. And so in conclusion, it is a lot more complicated than how do we teach abstraction, and naturally, because everything is bidirectional transformations, teaching and learning about abstractions involves bidirectional transformations as well. Now, when I was originally given this invitation, I think one of the pieces of background and something that we discussed that I might talk about was some work that I've done teaching about bidirectional transformations to 10-year-old children. And I would have loved to talk about that, but actually when it came right down to it, I don't understand that well enough yet to talk about it. I don't really have enough to say because I've not done it often enough yet. So ask me in 5 years and then I might have something to say about how you teach bidirectional transformations to 10-year-old children and why you should do so, but not right now. And then I'll go on and I'll take any questions or comments. Of course, in this recorded version, that'll have to be by email, but there you go. Thank you.